We're going to be continuing on and speak about the linear programming topic that we started off in the last lecture. And but most of today's lecture will actually just be for fun. Okay. The topic we'll be talking about in most of the lecture today, which is algorithms for AI and machine learning. I'm not going to test you on that, okay? Because it's going to be covering a whole bunch of topics, and in a very somewhat superficial manner. You actually need to have a whole course on AI and deep learning to be able to understand some of these algorithms. So it really won't be fair for me to test you on those topics in the final exam. But I hope you'll learn something and it'll sort of trigger your interest in some other areas, perhaps. Okay, so let's start by finishing up our talk on linear programming. So this is a quick recap of what we already spoke about. So linear programming, you're basically trying to optimize something, and you basically have a bunch of constraints. And those are all based on linear relationships. Both the outcome as well as the constraints are all linear, and that's why it's called linear programming. Of course, you could have a more complex case where you have quadratic programming as well, for example. So that's not typically taught, but if your constraints were not linear and were quadratic, or your optimization function was based on a higher polynomial of the decision variables that we spoke about last time, then of course it would not be linear programming. Okay, but that is certainly something that is of interest and is actually to some extent covered in AI and machine learning, where you don't necessarily have everything to be nice and linear. Okay, and perhaps we'll sort of give you a flavor of that when we start talking about AI and machine learning and deep learning algorithms. Okay, so in the linear programming example that we saw in the last lecture, where we had basically a company which is making two types of products, product one and product two. It had a price for each one of those products, which was different. And it had a bunch of constraints. And it said, well, product one requires 2 hours of labor of type L1 and 1 hour of labor of type L2, and product two had a different mix. Okay, so it only required 1 hour of each one of those types of labors. And there were other constraints, for example, how many hours of labor of type 1 of L1 was available in the market, and how many hours of labor of type 2 was available in the market in a given week. And so you had a whole bunch of resource constraints, which we wrote down as a bunch of linear equations. And we said, well, we're trying to optimize or maximize our revenue. And so because we have $3 for product one and $2 for each of product two, and so we have a simple equation for the profit, which is again a linear equation in X1 and X2. Okay? And so we said, well, how do we solve this? Well, first of all, you need to be able to convert that into a linear program. Okay, now in a linear program, you have you try to maximize or minimize a certain function, and subject to a whole bunch of constraints. Okay, now there are certain standard forms which are generally of the following form, that you're trying to maximize something, and you have a bunch of constraints which are all less than equal to something. Okay, so so what happens if you're trying to minimize something? How would you convert that into maximize function? Right, so you're trying to convert that into a standard form, which, as I said, has a maximization objective function. But let's say you're trying to minimize the cost. So how would you convert that into standard form? Yeah. Yeah, you just negate that, right? So if you have something which you're trying to maximize, then in fact you have a cost function which you're trying to minimize. So if you take the negative, you just negate the cost, then you're trying to maximize that, right? So so a lot of times you can simply convert a problem into a standard form, and then that standard form can be fed into a standard library, which works on the standard form for linear programming. What happens, for example, if some of these constraints are of the following form: x1 is equal to 100. All right, so let's say that we have a non-standard form which is based on equality rather than inequality. So can we convert that into a standard form which says that you can convert that into an equality? Yeah. Sorry? Substitute what? No, so the standard form is accepting variables, decision variables. And so you need to work with decision variables with certain constraints. So subtracting those constraints and putting in constants would not be acceptable. You still need to have, you can increase the number of constraints. So instead of x1, you could have x2 and x3, which could replace x1. So is there some way to convert an equality into two inequalities? Yeah, so you could convert it into two variables, and one of them could say that it's less than or equal to 100, another could be the negative of that could be greater than or equal to 100, right? So that sort of, so there are ways of transforming some of these equations into standard form. But the tricky part actually is simply to take a write-up, okay? So to take something like this and to be converted into a linear program, okay? So that's something that I might give you on exam, all right? So I might give you, a description of a problem, and I'm not asking you to solve it, but I am asking you to convert it into a linear program. Okay, so you need to be able to convert that into a bunch of equations, to linear equations and maximization of some equation. You may also be asked to draw a two-dimensional graph, something simple. I don't think that's too difficult for you guys. So those are the kind of problems that you could come up. Hopefully, I'll give you some sample questions before the end of the week, before early next week. Your exam is on Thursday, so you'll have a few days, hopefully the weekend, to practice some of those questions. I will give you the solutions as well. So, and here's an example from the CLR, it's from the book. So it's a very similar kind of, but it doesn't start off with a description. It simply starts off with a bunch of equations. Okay, so it's generally useful to start off with a description of a real world problem and then to convert into equations, which is not what CLRS did. So that's why I gave you my own example. But as you can see, each one of these constraints can be converted into a bunch of lines, and each one of those lines will give you a region where you have the feasible region. So this is the feasible region. And then you can have the optimization equation sort of, draw it out as, equalities. And then you can see that as you make the profit or the revenue, whatever you have, the objective function to go further and further, at some point it will end up at one of these vertices. Okay. So if you start off at this particular vertex, you notice that you'll probably end up at this vertex first, and then it'll go up to that vertex. Okay. So as I mentioned in the last lecture, that in all of the linear programming problems, if you have, and we started talking about something exotic, I started talking about three-dimensional structures, and eventually I ended up with God as well. Okay, that was just a side. Okay, but you can sort of try to visualize what a three-dimensional object would be looking like, and if you had instead of just two or three decision variables, if you had four, you'd have a four-dimensional space. If you had five, it'd be a five-dimensional space, and that becomes extremely impossible to even imagine. Okay, so there are solutions to this, and one of them is called the most famous method for solving this is called the simplex method. And it's a little tricky, but basically the idea is as follows. You start off by looking at the basic vertex, which is generally the 0, 0 point. Okay, and I'm showing this for a two-dimensional space. So here you only have x1 and x2. You only have two decision variables shown as in the standard graph. And so you start off at 0 point at the starting vertex, which is 0, 0. And then the simplex method does a whole bunch of manipulations using those linear equations, which I'm not going to go through. And eventually it figures out the first vertex to go to, okay, and then a second vertex to go to, and eventually it traverses through all the possible vertices, okay? Now, in a two-dimensional case, how many vertices could you actually have, and what would it depend on? So I said that you have n decision variables and m constraints. So which of these two variables would the number of vertices depend on? Or would it depend on both? But would it also depend on m, the number of constraints? So in this case, for example, we had several constraints. We had this constraint here, we had another constraint here, third, fourth. So you can see that the number of constraints is sort of defining the geometric shape that we're looking at. And if you had a lot more constraints, then the number of vertices would increase. Even though you just have two variables, but the number of constraints would determine the number of vertices, okay? So the simplex method simply goes through all of the vertices not in a brute force manner, but in somewhat of a, there's a methodology to this. And generally it finds the solution in polynomial time, in n, okay? The brute force method would actually be to the power n, okay? So, so this is supposed to be what is referred to as an NP-hard problem, which is essentially an exponential problem. And here are a couple of examples, the basic one example, and this is the case where n is equal to 3. So you have a three-dimensional space, x1, x2, and x3. So you have three decision variables. But as you can see that the number of constraints is probably a lot larger. Okay, so each one of these, the planes which are intersecting this three-dimensional space is actually a constraint. Okay, so if you have M to be relatively large, you can see that this three-dimensional space will have a lot of sides to it. And then the simplex method would start off, let's say, at a starting vertex, and it would simply go through the edges of this shape, at least in three-dimensional space. So you can see that it's going through one vertex to another, and at every point, it's essentially figuring out what is the value of the maximization function, okay? And then based on that, it's doing some manipulations, and it's heading in the right direction, okay? It's not going to brute force in a brute force manner, explore all the possible vertices, because that would be order of 2 to the power n, okay? And that would make sense. So it does it there's a certain methodology to it, which sort of makes it go towards the optimal direction in a relatively fast manner. In this case, relatively fast simply means that it's polynomial as opposed to exponential time, okay? So that's basically the whole simplex method. And interestingly, there are new solutions which have come up, which actually, instead of going through the surface of this geometrical shape, it actually goes through the inside of the space. Okay, and those are some new algorithms which come in. So instead of going through this surface, it sort of goes through the inside of the space, and so it's able to get better and better solutions. And these were some relatively recent discoveries or algorithms which came up, which made a big difference, because linear programs are, as you can imagine, they have a lot of applications in real world operations research. So that was the quick topic on the linear programming and simplex method that I want to speak about. And then let's on to AI and machine learning algorithms. Okay, so again, as I said, I'm not going to cover this, but hopefully you'll get something out of this interesting topic. So let's talk about AI in general. And if you want to learn more, there are a whole bunch of videos. I've taken this particular slide from the following video, which is a nice 10, 20-minute video on general field of AI versus machine learning versus deep learning. So if you think about the general area of AI, and you think about how is machine learning related to AI, well, that's a subset. And then one of the most popular areas of machine learning these days is deep learning, which is again a subset of machine learning. Okay. And so let's take a look at some of the algorithms so that you have a slightly deeper understanding of not just deep learning algorithms, which are the rage, but also the traditional AI algorithms. And so there was a lot more to AI and machine learning than deep learning. Although today everything seems to be dominated by deep learning, but there was a lot more to it. And so you need to be able to see what were those traditional algorithms and how and are they still being used or not? And in fact, these are. So one of the algorithms that I really liked were evolutionary algorithms. Okay, and a lot of these AI algorithms are in fact somewhat derived from biological systems. Okay, so this obviously evolutionary algorithms is derived from the concept of evolution, and it's sort of some of these basically mimic biological systems. Okay, so the evolutionary algorithms basically are based on the basic concept that you generate some population and you test that population. Okay, and then you recombine parents. Okay, and you do some mutations. You look at their genes, you recombine their genetics, and you do some mutations, and you come up with some whole bunch of offspring. And then you test the offspring, are they better than the original parents? Okay, and so you come up with a whole series of generations, and eventually, after hopefully a lot of iterations, you come to better and better offspring. Okay, so that's the basic concept of evolutionary algorithms. So let's take a deeper look at one of the problems, which is a very sort of a simple problem, and it's a puzzle. So this is called the n-queen problem. Okay, so the idea here is that you have an n by n chessboard. Okay, and normal chessboards are 8 by 8, but normally you just have a single queen. In this case, you have n queens. Okay, and I hope everybody has played chess, right? Yeah, so you know how queens interact. So queens can challenge other pieces either horizontally or vertically or diagonally as well, right? So the idea is that you want to place these n queens in such a manner that none of them threaten each other. Okay, seems like a crowded space. But yes, you can have, in an n by n board, you can have n queens and arranged in such a way that none of them challenge each other. Okay, so just out of curiosity, can anybody identify how many of the pairs over here are challenging each other? And which ones are they? Is there more than one pair, or then none of these are challenging each other? Somebody who's recently played chess? Clearly, for example, these two are not challenging each other. These two are not. These two are not. These two are not. No, no, no. Yeah, you can see these two guys, right? So these two guys are challenging each other. So in this particular case, you have one pair of queens which are challenging, which are threatening each other. Okay. Now it so turns out that this is a horrendously complex problem to solve. So if n goes to, let's say, instead of 8 by 8 goes to 10 by 10 or 20 by 20, yes, question. Yes. So most of these are NP-hard problems, and these are a class of algorithms called combinatorial optimization problems. Okay, and this is certainly, I mean, this is really bad. N to the power n. Even if it was 2 to the power n, that would be bad, but or some k to the power n. But this is n to the power n. Okay, so this is extremely difficult to solve in the traditional manner. Okay, So here's where genetic algorithms can be used. Okay, so evolutionary algorithms, and a subset of evolutionary algorithms are called genetic algorithms. And basically, the idea here is that you're going to use the concept of genes. Okay, so it comes from the genome sciences. So when you have these functions, you start off with something called a heuristic. Okay, it's an approximate function which may not give you a hardcore solution, but it'll get you somewhere close to the solution. Okay, so even if you get a close to optimal solution, sometimes it's fine. Okay, you may not have the perfect children, but if you have near to perfect children, you know, us beings are probably reasonably close to being perfect, but you know, hopefully at some point we'll become even better. But you need to do with what you have. So with genetic algorithms, even if you have a suboptimal solution, that's also fine. Okay. In this case, the heuristic is called a fitness function, and we'll talk more about heuristics in the next example. So this fitness function is basically describes how good is the solution. Okay. Now you could have a whole bunch of different fitness functions you could define, but in this case, we're going to define a fitness function, which is the number of non-threatening pairs of queens. Okay. So in an 8x8 board, the maximum number of threatening pairs could be 28, right? That's 8 times 7. That's the number of pairs that you can have. Okay, and divide by 2. So that's 8C2. So that's 28. The number of non-threatening pairs could at a maximum be 28. All right. So all of them are non-threatening, which is the ideal situation. In this case, the example that I gave you, that only has one pair threatening. Okay. So this fitness function is f is equal to 27, right? So it's almost close to perfect. And if somehow you could rearrange this to get even these two to be, which is generally not easy. So, I mean, if you imagine, if you just try to do it manually, I mean, I haven't tried it, but it seems kind of difficult, right? I mean, I can't see where to fit this on this particular column. There is some other queen which it will threaten. Okay, so you can see that's not a trivial problem to solve. So let's see how genetic algorithms will solve this. So we need to come up with basically an initial population. Okay, so the population will be a whole bunch of possible parents. Okay, and what we'll do is we'll select some of these parents based on the fitness function, and then we'll generate their offspring. Okay, by combining these parents in a couple of ways. We'll sort of do some kind of genetic crossovers. Okay, take their genes, we somehow define their genes and do some kind of crossovers, and then we'll do some kind of mutations. Okay, this sort of hopefully resembles real-world evolution. Okay, and then we'll take a look at the offspring, and we'll say, well, let's select the offspring which are better. Okay, so better in terms of that fitness function, and so that's called the survival selection. Okay, so comes out straight from Darwin's theory. And then we'll take these offspring, and then we'll sort of introduce them to the original population. So the original population, we'll maybe take the best of that, remove some of the lower parents, the original population, introduce the better offspring, and hopefully, and then we'll continue doing this iteration, keep on doing it until perhaps we have some kind of a termination clause which says that, you've run out of time, or, you found the perfect solution. Okay, so here is a way to construct a gene. Okay, so here is an identification or an ID that you could say depicts this particular chessboard position. Okay, how have we done that? Well, we've taken this particular location, but you've said that the first queen is at a location of 1. The second queen is at a location of 2, 3, 4, 5, 6. All right, so this is 6. The third one is at location 2, and so on. Okay, so you've got 8 of these queens, and each one of them corresponds to a number which corresponds to its location on the chessboard. So that's how you start off, and you design a gene for this particular problem, this particular example. And then what you do is you take maybe 2 parents, okay, 2 randomly chosen chessboard configurations with randomly allocated queens to them. Okay, but each one of them has 8 queens. And we combine these in some manner and create an offspring. Okay. Now the question is, how do we combine these together? Well, what we'll do is we'll take their genes, so to speak. Okay. We'll take both of their genes, and then we'll cut the first, some portion, somewhere in the middle, some randomly located location. We'll take some portion of the gene from one parent, okay, and the rest of it from the other parent, okay? And we combine this to form the new gene, okay? So 327 is coming from here, and this is coming from here, and now the blue and the yellow combine to form the green chessboard location. And in addition, we do some kind of mutation, okay? So we can take one of these locations corresponding to maybe the third location, and we randomly change that to some random number. Okay, so this has been changed to number 5, I believe. Okay, so now you have 552 instead of 152. So that's how you're creating the offspring, right? Now you need to apply the fitness function to be able to figure out how good is the new offspring, and you also need to be able to select which parents to actually use for for generating the offspring. Okay, so here's let's say you've got 4 parents. Okay, so these have been randomly generated. This is the initial population, and then we have the fitness function. So this corresponds to the number of pairs which are non-threatening. Okay, so if you do the calculation, hopefully you should be able to get to 24, which means this is better. The blue one is better than the yellow one, which has a fitness function of 23, and then some of these are really bad. Okay, so the way they've selected the parents are they've selected the top 3 out of the 4. Okay, based on the fitness function, and then they've generated 4 children based on a combination, a random combination. So these 2 have been generated based on a split over here. Okay. And then these 2 parents have been combined together by doing a crossover at this particular juncture. Okay, and so you've generated 4 offspring, and then you've done mutation on each one of those offspring. Okay, so you've done mutation. Some of these you haven't done a mutation. Some of these you've done some random mutation. Okay, and so once you have a whole bunch of offspring, then what you can do is you can calculate the fitness function on those offspring as well. Okay, and then you'll go back and select the best of the offspring and maybe some of the best of the population, the original population, and combine the offspring with some of the parents, and you keep on doing this iteration over and over again. Okay, so this is one way, and I'm not showing you any results here, but genetic algorithms have been known to give you some quite nice results. Okay, so on very difficult problems, you can apply this to a whole variety of different algorithms. Okay, you can think of how you can create a genetic algorithm on any particular problem. You can define it the way you want to, and you can come up with your own genetic algorithm for a given problem. Okay, so let's take a look at a different class of similar, perhaps, problem, and this is called an 8 puzzle. Okay, so an 8 puzzle is yet another, and so this is a classical AI algorithm. Okay, this is not a machine learning algorithm. This is not a deep learning algorithm. This is the original AI. Okay, and here's another original AI problem. So this is called an 8 puzzle. Okay. It doesn't have to be 8, but in this case, we start off with 8, which basically is a 3x3 grid. Okay, and one of these grids is empty, which gives rise to the number 8 because it's 9 minus 1, 8. So you have 8 numbers, distinct numbers, and the goal is basically to be able to rearrange the blocks so that they are in order. In other words, 1, 2, 3, 4, 5, 6, 7, 8, and the blank block is right at the end. So that's the objective. Okay, and what you can do is the possible actions are that you can move this particular block in one of 4 directions: left, right, up, or down. Okay, so in other words, if you move this to the left, 5 will come here. If you move it to the right, 6 will come in the center. Okay, Now, it turns out that this is again a horrendously difficult problem to solve. Okay, so if you have a 3 by 3, in this case, you have 9 factorial possible states. If you have a 4 by 4, you have 10 to the power 12. If you have a 5 by 5 grid, you have 10 to the power 25. Okay, so you can see that it is an extremely difficult problem to solve using any traditional algorithm. So what do we do to solve this? So now you could come up with a genetic algorithm for this as well, but let's use a different type of algorithm. Okay, so here's a search based on sort of a tree search. Okay, so we say, well, we're starting off at this particular location, and then we'll say, well, what are the possible ways in which you could progress? Okay, so you could possibly go in one of 4 directions, right? So you could go left. So this block goes left, and so 5 comes in the middle. You go right, 6 comes in the middle, and so on. Right? So you go left, right, up, or down, and this would result in 4 possible solutions. And then each one of them could possibly have 3 or 4 possible solutions. Okay, based on where the empty block is. Okay, but again, this is going to result in a humongously big tree. Okay, with 3 or 4 children every time. And so if you try to do a brute force search, then obviously you're not going to end up anywhere. Okay, so another class of algorithms, basically, as I mentioned, uses heuristics. Okay, as I mentioned, the heuristic in the previous example was the fitness function, right? Now we're going to come up with a heuristic which sort of gives us how good is the solution. Okay, so we can define perhaps 2 different heuristic functions. Okay, and the first one is, let's call it H1. It says the number of misplaced tiles. Okay, so this is saying, well, how many of these tiles are actually in the wrong location? Okay, so that's a different heuristic. In this case, it seems to be 7. So 7 of these are in the wrong location. You can probably figure out that there's one of these which is in the right location. 1, 2, 3. One of them is in the right location. A second heuristic could be the sum of what I call Manhattan distances. So people who lived in New York, Manhattan, know what the Manhattan distance is. Everything is in a grid. So if you want to go from location X to Y, you either have to go this way and come down. There are no, except for Broadway, I think most of the other roads are either vertical or horizontal. Okay. So Manhattan distance basically says, well, let's figure out for each one of these, how many spaces does it need to move in order to get to its right location. Okay, so each one of these, so the second one is actually in the right location already. Okay, so it doesn't need to move, but the first one needs to go 4 paces. So probably it needs to go up to 7 over here. So it needs to go 1, 2, 3, and 4. Okay, or this way. So you can figure out that these are heuristics. Now, a heuristic doesn't really guarantee that it's a very perfect fitness function. Okay, it's just a heuristic, and you could come up with your own heuristic, which is saying an approximate function, which sort of, if you try to maximize or minimize that, it'll sort of take you in the right direction. Okay, so these heuristics are very useful, and they're often used in AI algorithms. Okay, and so if I use these heuristics and then try to use applied on using the tree search, then you could have, for example, you start off with a heuristic of 14. Okay, this is probably based on the Manhattan distance. And then you could say, well, if I go in the left direction, my new heuristic is 13. If I go down or to the right, these are the new heuristics. So it sort of is telling you which direction to go in that search. Okay, which direction would you go in this particular case? Clearly in the direction of 13, right? Because it's reducing your heuristic, which is your optimization function. You're trying to minimize that. So this is saying that you have 14 of these tiles which have to be moved. And this is saying, well, only 13 have to be moved. Okay, is that a question? Yeah. Yes, so that's exactly what I'm going to show you in a few minutes. All right, so you've already seen what the problem could be. So you could have a situation where in this case it's really obvious that you have 15, 14, and 13, and so 13 is the direction to go. Okay, so you can sort of say, well, that's going in the right direction. But it's quite possible that you could have this particular situation. So I'm showing you on the vertical axis the heuristic, and you could have a problem where you're stuck in the local minimum. Okay, so here's an example where you have h is equal to 14, and the three possible options all give you the same heuristic. Okay, so you have no way to go. You don't know which direction to go in. Okay, and this is sort of saying that this is clearly an optimal solution. However, you're stuck at a local minimum, and in order to get to an optimal solution, you'll probably have to go in the wrong direction. Okay, so you have to sort of climb up a hill in order to get to the right valley, which may be at some other location. Okay. Now, how do you get out of this? How do you get out of a local minimum? Okay. Suppose you are over here. Now, there it'll be kind of obvious which direction to go into, right? Because you'll have a heuristic which is saying this is the way to go. Okay. And this is not the way to go. But if you're stuck at a local minimum, it's not clear which direction to go into. Okay. So if I were to give this to you as a problem, can you come up with a way to get out of this valley? And if anybody has actually done trekking, you know how to get out of this, right? So you know that you may not have a GPS and you're in the middle of the Nevada Valley and you're trying to get to your maybe a nice cozy spot and you're stuck in the valley. And so what would you do? Yes. Yeah, so that's a good solution. So what you could do is you could say, well, let's start at different locations. So I could randomly select a whole bunch of possible solutions and then see and try all of them. Okay, and perhaps one of them will lead me to a minima which is better than all of them. And that's a great solution. It's a fantastic solution. So and there are algorithms which are actually based on that. Okay, which I'm not naming, but yes, there are algorithms which are sort of similar to the genetic algorithm that we started talking about, right? You're generating a whole bunch of population and you're saying which ones will actually get to generate better solutions. Yeah. So there could be other solutions as well. Can somebody think of other ways of getting out of this problem? So, you could generate a whole bunch of solutions based on seeds, as was suggested, which would generate, you start off at different points. And suppose you generate a seed over here, and this one will definitely give you a better solution. And if you had a seed over here, which generated a random number over here, this would get stuck in the local problem, but this one or this one would definitely give you a global, perhaps a global solution. But other ways of getting out of this problem. I mean, think about it in a physical sense that you're stuck in a valley and how do you want to get out of it? Yes. Say that again, speak a little bit louder. Yeah, so you could go upwards, okay, until you get to some other location, and then you start downwards as well. So you sort of go in a random location, but would you want to go in a random location, or would you? So suppose there's a three-dimensional structure in the valley, and here's one mountain, here's another one, third one. Which direction would you tend to go in? Did you take the steepest one? Probably not, right? Anybody has done some real trekking, you'd probably not want to go in the steepest direction, right? So you probably don't want to go in this direction. If I look at the gradient of these, perhaps if this one is a lower gradient, you might imagine that, yes, it seems to be more appropriate to take a lower gradient, right? But again, you could come up with solutions which may not make sense. So yeah, there are different ways that you could pick a better solution. But let's take a look at a solution which is often used, okay? And this is called a gradient descent, okay? So basically what you do is you say, well, let's take a look at this particular point, all right? And I'm trying to find, and this is a slightly different problem. In this all we're saying is that this is a simpler problem. All we're saying is that we just need to get to the optimal solution, and we're assuming that the local optimum is what we're trying to search for. Okay, and we're going to assume that this cost function is a continuous function, which can be differentiated and a gradient can be found. Okay, so I'm sure that you've come across this in calculus, but basically what you could do is, if you want to get to this optimal solution, okay, where y is minimum, all right, and you're starting off at this particular place. Does anybody know the solution to this particular problem? How would you generate an iterative solution to get closer and closer to the optimal solution? I'm sure that somewhere in some calculus course you should have come across this. So it requires finding the gradient. Okay, so what you assume is that you can take this function, that it's given to you as a function, okay, and you can find the gradient of that function. Okay, and so this is what you do. You basically take the derivative gradient of that function. Okay, you take the original function. So let's say that you're at location 11, all right, and you're trying to find the x star, which is the solution, the optimal solution where y is minimum. So let's say you take the gradient over here, which is a negative gradient. As you know that gradients which are positive will look like this. Gradients which are negative will have a negative slant to it. Okay, so let's assume that you're starting off with the negative gradient of 2. Okay, so here's this function which will allow you to get closer and closer to the optimal solution. Okay, so can somebody tell me what this would generate us? So xn plus 1 would be xn 11 minus the gradient minus r. So we're going to use a learning rate. Okay, that tells you how fast you want to get to the destination. Okay, so we're going to use a learning rate r of 1. So 1 times the gradient. Gradient is minus 2. Okay, and that gives us 11 plus 2, which is 13, 14. All right. Can somebody do the next one? So let's assume now the new gradient over here that you've got into this particular location, which is now 14, and the new gradient over here is minus 1. So as you can see, the gradient will keep on become smaller and smaller, right? Because eventually at this point, what is the gradient of this curve, of this line? When you have the optimal solution, the gradient of that is 0, right? But as you're getting closer to it, you can imagine that the gradient becomes smaller and smaller. So initially, it'll be really large, it'll be smaller, and as you get closer to the optimal solution, the gradient will become smaller. So now, essentially, will you be taking larger and smaller steps? So the next one will be 14. All right, take the old value and minus the new gradient, minus the learning rate, which is 1, multiplied by the new gradient, and that comes out to be 14 plus 1, 15. Okay, so you can see that as the gradient becomes smaller, this iterative function will take us closer and closer to the optimal solution. Okay, so here's a few iterations. In the next iteration, let's say it gets to did I skip one step? So yeah, 11 plus 2 is 13, not 14, right? So we got to 13, and then we got to 14, and then let's assume that the slope becomes smaller and smaller. So the new slope over here at 14 is even smaller than minus 1, and becomes 0.5, and so on. So you get the idea, right? So you'll be taking smaller and smaller steps to get to the optimal solution. So this is a very popular algorithm, which is called gradient descent. Okay, and this is actually at the heart of, you may not realize it, but it's the heart of deep learning. Okay, so and hopefully I'll get some time to talk about deep learning. So that's why I'm taking a bit of time to talk about this, because this is used in neural networks all the time. Okay, so what happens if the learning rate R is too small? Okay, because you're multiplying the gradient with R, it takes very small steps. Okay, so you may take forever to get to the optimal solution. But if the learning rate R is too large, okay, then what happens is you take too big a step, okay? If you take too big a step, you end up over here. Now, what's going to happen over here? You're saying xn plus 1 is equal to xn minus r times the gradient, okay, dx by dy. So what's the gradient going to be looking like? Will it be a positive number over here or a negative number here? So the gradient over here was a negative number, let's say -2. The gradient on the other side of the curve will be negative or positive? Should be positive, right? Because negative gradients are like this, positive. So this gradient is going to become a positive number, let's say +2. You're multiplying it by an r, which is again a positive number. So now you're going to decrement xn. Okay. So based on the gradient, you're actually start going forward initially. If you go too far ahead, you're going to go backwards. Okay. So you're going to go backwards and forwards, and eventually, hopefully, you're going to end up at this particular spot. Okay. But if the gradient is too large, really large, you can imagine what's going to happen. You may jump from here to a larger spot, and then you're actually diverging. Okay. So the gradient is too large, you may actually diverge and you may never find a solution. Okay. So in deep learning, it's important to be able to choose this gradient. And let me just show you right away an online site which sort of allows you to play with deep neural networks. Okay, so if any of you want to play with this, it's called playground.tensorflow.org. Okay, and it allows you to play around with these different variables. So here's the learning rate. Okay, so if I make the learning rate really small, it's going to take forever to converge. If I make the learning rate too large, it may diverge. Okay, but you want to understand this right now until I actually go a little further. So, but that's just to show you that yes, you can actually play around with these things. It's quite interesting. So those are fictitious problems, but in a real world problem, the actual cost function may look something terrible. Okay, so this is a real world function in which you have hundreds and maybe thousands of local optimum, and there could be one global optimum solution, which is extremely difficult to find. Okay, and you could try different ways of finding the solutions, but generally this is the big problem. How do you find an optimal solution? So there is no simple solution to this. Okay, and this is again a research problem, and researchers are of course coming up with new and new, better and better algorithms all the time to find a local optimization, to find an optimal solution. So you might have come across these. These are the typical machine learning techniques. Okay, so some of these are called supervised. This class of algorithms which are called supervised learnings. There are unsupervised learning techniques. There are semi-supervised. There's reinforcement learning. What do those mean? Okay, so if I take you through this particular picture, well, unsupervised learning generally means that there is no human intervention. Okay, you just give it a bunch of data and you let the algorithm sort of come up with a solution. All right. In supervised learning, you're basically providing it solutions. It's sort of what we do in exams, right? I'm sort of giving you, every time I give you a solution to a problem, I'm doing supervised learning, right? Because I'm telling you, here's the problem. First try to figure it out yourself. And then here's the solution. And then you were trying to say, well, I got a different solution and here's the actual solution. And you compare the error, and the error is based on the actual solution minus what you got. And then you try to minimize the error, right? So you try to come up with a better and better solution so that your error is eventually 0 and you get full marks, full points for that particular question. So that's an example of supervised learning. Reinforcement learning is yet another category. And there, basically, what happens is that the algorithm tests out different solutions. Okay, so it's like, you give them a problem and it says, well, here's a solution. And then it gets feedback. It gets automatic feedback. Okay, and that feedback tells it, whether it's getting close to the actual solution or it's getting away. Okay, and so that continuous feedback will eventually give it, lead it towards the right direction. But the feedback is based on its guess. Okay, and that's why it's called reinforcement learning. It's sort of like playing a game. Okay, so it's playing a game, and then it's seeing how many points did it get if I move the paddle in one direction versus the other, and then it figures out what to do in the future based on a whole bunch of feedbacks. So let's give you some real examples. So this is my own personal Google Photos page, and these are a couple of my grandchildren. That's my son. That's my ex-boss. All right. So those are the people that come up in my Google search. Now notice that if I went into people, okay, these are 4 faces that just pop out. Okay. Now, can you think, is this supervised, unsupervised, or reinforcement learning? How did it come up with those 4 faces? Basically, based on all my photographs, all right, thousands of photographs, which are in Google Photos, it automatically selected that these are the 4 individuals which are perhaps appearing most in my database. So is that based on supervised learning, unsupervised, or reinforcement learning? How did it actually figure it out? Now, I didn't actually go ahead and label all of them, all right? So what does that indicate to you? Clearly, it wasn't supervised, right? I didn't have time to actually say, well, these are all my grandkid number 1, and these are all my grandkid number 2, and these are all my bosses, and this is my son. I didn't do that, right? It automatically was able to identify based on all those thousands of photographs that these are sample images, and it differentiated between my boss and my son, right? It didn't give 2 pictures of my boss. It only gave me 1 picture of my boss and only 1 picture of my son. And these 2 are 2 separate grandkids, right? So basically what it did was it did a bunch of unsupervised learning. You didn't have to train it. All it did was it was able to automatically differentiate between different faces. So when it saw 2 faces which looked alike, it sort of clustered them. Okay, so all the pictures which looked alike, which looked like my son, were sort of in one group, and all the pictures which looked like my boss were in a separate group. And I was able to differentiate that this is a separate person. It doesn't know what the name is or what the relationship is, but it knows that this is a different individual as compared to my boss. Okay, and that my son, my grandkid number 1, is a different individual from my grandkid number 2. Okay, but it's not always perfect. So there are examples where sometimes it gets confused. Okay, and when it gets confused, what happens? Has anybody come across that in Google Photos? What happens? Yeah, Jane. Yeah, it asks you to differentiate, right? So it says, so this was example of unsupervised learning. This is based on example of concept of clustering. It's basically clustering the photographs together, which look alike to it. And here's an example of supervised learning, right? So when it says, well, here are 2 photographs, not very clear to you right now, but there are 2 different. Actually, these are 2 same students, 2 of my students. And it's trying to say, well, are these 2 the same person? Okay, so it's confused. So now it's supervised learning. So it's kind of mixing unsupervised learning with supervised learning. And as soon as you say, well, these are the same persons, that's where you're providing it feedback. And that's where it's actually combining the 2 concepts together. Okay. So, so that's why, and Google uses this all the time, right? In fact, every time it asks you to figure out whether you're human or robot, it gives you pictures and it says, well, identify the traffic lights in this, right? It gives you a bunch of pictures and you're supposed to identify the traffic lights or cars or automobiles, right? And you select those. So you're actually helping Google in its database. It's actually helping Google identify, do the classification. So you may not realize it, but it's like you're actually, you're part of the game, so to speak, okay? So it's because most of the time people are right. Okay, sometimes they're wrong, but majority of the time people are right. So actually they're identifying which of these pictures are traffic lights versus non-traffic lights. That's how Google uses that for supervised learning. So you guys are the supervisors. You can do a lot more, right? So you can actually do, for example, a search based on word search. So these are photographs that I have, and I said I want to find all the photographs which have birds on water. Okay. Now I didn't actually go in and label each one of these photographs, but it knows the concept of what a bird is because somewhere it's been supervised learning. Somebody's identified what birds look like and what water looks like. And so it knows what a bird is, it knows what a water is, and can identify based on your own set of photographs, it can identify all the pictures which have these two characteristics. Okay, it's pretty smart. You can have captions. Okay, so you can just give it a picture and you can ask it to do a caption. So one of my students just did a PhD recently, and what he did was he improved this captioning technique, and he was able to actually have adverbs in it. In other words, for example, or positional location. So for example, if you were standing in front of a fence and there was a small horse behind you, it could tell you that here's a human being, there's a person, a boy or a man, standing in front of a fence. So it could be able to figure out that the fence is behind it. And the fence, and behind the fence, there is a small pony. So it could do all of that, okay? So these techniques are continuously being improved, okay? He's just about to defend his thesis, hopefully in the next month or so. Then you have a lot of other examples. You have recommendation engines. You use that all the time. When you go into YouTube, it gives you a whole bunch of recommendations. So all of these are using a class of algorithms which are now called deep learning, okay? Natural language processing, all these LLMs, your chat GPTs and lambdas and so on. All of these are now based on a whole class of algorithms, self-driving, okay? All of these are based on deep neural networks, okay? So this is what's going on today. Almost every algorithm that you can think of which is doing something interesting these days is all based on the concept of deep neural networks, okay? So I have about, let's say, 15 minutes. So let's take a quick look at what deep neural networks is, all right? So again, it's biologically inspired, okay? So it's based on our brains, the most sophisticated organ perhaps that exists, okay? And the human brain has about 100 billion neurons, okay? Now, what is a neuron? So each one of these is a cell, okay? It's called a neuron. There are 100 billion or 10 power 11 of these. So depending on which mammal you're looking at, for example, an elephant may have smaller or larger number of neurons. Sometimes even really small creatures have a large number of neurons. So it does depend on the sophistication or perhaps the brain power or lack of it in some cases. So it does give you some indication of the complexity of your brain, okay? Now, the neurons are, think of it as a graph, okay? These are the vertices, the nodes. Now, each of these neurons can be connected to perhaps every other neuron, okay? So how many interconnections, how many edges would this graph have, okay? So if it could connect to every other neuron, that would be how many edges in this graph? It's a graph problem. If you have 10 power 11 vertices, nodes, and it's a dense network, if it's extremely dense, all your neurons are connected to every other neuron. How many neurons would that be? 10 11 squared, right? So that's about 10 to the power 22. So this is potentially how many interconnections or what are called synapses, okay, that you could have. Now, it so happens that humans don't have that many synapses, okay? Synapses are these links, okay? So you generally have, if you have 10 to the power 11 neurons in your brain, you only have about 10 to the power 14 synapses. In other words, every neuron is connected to about 10 to the power 4 other neurons. So would you classify this as densely or sparsely connected network? So it's not going to be dense, right? It's going to be sparse, simply because a dense network would be something like 10 to the power 22 edges. But so the brains actually, there's a lot of potential. And so when you're born, you can imagine that you have the same number of neurons. So you still come up with 10 power 11 neurons. But you can imagine that the synapses, which are the interconnections, are very few. So a child which has just been born may not have 10,000 interconnections. It may only have, let's say, 1,000 connections. But as it learns, okay, as every time it touches fire and it realizes this is hot, I'm not supposed to touch it, and eats ice cream and says, I love it, it's learning, okay? And that's when those neurons, those synapses are, the interconnections are being formed. So as you become older and older, you get more and more synapses, okay? That's your learning process, okay? When you become really old and your grandparent stops learning, what happens then? They actually get into a stage where their synapses can't form. They can't form new synapses, okay? And that's what happens when, you tell them your name and 2 minutes later, they forget your name because they can't form new synapses, okay? So that's a little bit about the human brain. Now, how is that replicated in neural networks? Well, basically we say, well, let's take a single neuron, okay? So here's a neuron. And here's another neuron. And this is the actual biological term, which is an axon, okay? And we're going to make a very simple model out of that, okay? We're going to simply model that as a single, what is called a perceptron, okay? Now I've got a whole bunch of equations there, but don't get too scared. So basically what we're saying is that here, the inputs to a neuron in the brain could be, for example, a sound. It could be a touch. Okay, so imagine these two inputs coming into a neuron. All right. Now, a neuron which is already trained, it knows that when this particular sound and this particular touch comes, I'm supposed to trigger a response. Okay. So imagine that this particular sound is the sound of your mother, and this is the touch of your mother, and that that indicates that you have a positive response. You recognize your mother. Okay. But if it's somebody else coming in, that may not trigger that response. Okay, so that's a well-trained neuron versus a not a well-trained neuron. Okay, so the way we train it in a neural network is basically you put weights. Okay, so we attach weights to these inputs, and the weights determine whether we're supposed to trigger based on those inputs or not. Okay, so if you want to be able to give a positive response, okay, so those weights are going to be strong. But if you don't want to give a positive response, those weights are going to become weak. Okay, you're going to make those really small. So that's the basic concept behind a neural network. Okay, it's a little bit more complicated, obviously, but in a 15-minute intro, that's the best I can do. So then you again use something called gradient descent, okay, on this, and you come across something called a neural network. Okay, so this neural network is sort of resembles, or it's a very simplistic version of any brain, whether it's any animal brain. Okay, it doesn't have to be a human brain, but basically what it's doing is taking inputs, okay, and each one of them can be, for example, a real number. All right, and then it's connecting it to other nodes, and basically each one of these has a weight. Okay, so there's going to be a weight 1, and then there's going to be another weight. So this could be over here weight NM. Okay, so each one of these interconnections has a weight, and that depends on the training. So if those weights are high, it means something else. If those weights are small, it means something else. Okay, now the depth of this determines how deep the network is. So initially, when neural networks people came up with it, the only difference between neural networks and deep neural networks is the depth to which how many hidden layers do you have. Okay, how many layers do you have? So if you just have a single hidden layer, then that's called a shallow network. And people have discovered that today, deep neural networks can really outperform shallow networks. Okay, so you just put in more and more layers of these. The number of neurons you can increase. The number of neurons can be different in every one of these layers. So for example, the example that I showed you earlier, you can play around with this right away, and you can form your own network. So for example, here is a neural network, which comprises of a single layer, okay? And I can reduce the number of neurons. So it's got two inputs, and it's trying to classify based on the inputs. So for example, it's trying to classify these two problems, right? It's trying to classify the orange dots versus the blue dots, okay? Now, if I start training this, here's what happens. It doesn't take very long to get trained. Now, how was this training done? It was based on a concept called backpropagation, okay? And it's based on supervised learning, okay? So in supervised learning, remember, you give it the correct answer, okay? You have and the correct answer is called labeled data, okay? So whenever you hear labeled data, it basically means that you're telling it that here is a picture. It's a picture of, let's say, an elephant versus a mouse, okay? And you give it thousands of these pictures, and eventually it figures out, well, these are all the pictures which were labeled as elephants, and these are all the pictures which were labeled as mice. And so eventually it starts learning that when I get a new picture, I can categorize, I can differentiate between a mouse versus an elephant. Why? Because I've been trained on a lot of pictures, okay? So it's been given a lot of labeled data. So when you get labeled data, basically what it does is it takes the input. So you can imagine that I've given it picture of an elephant, right? And the output of this is some numbers, okay? So a whole bunch of numbers come out over here. And these numbers perhaps are basically identifying one of different categories of animals, okay? So this one, for example, could be an elephant. This one over here could be a mouse, okay? Now what's happening is that you're going to give it labeled data, and it's going to calculate an error function, and then it's going to do something called backpropagation, okay? So backpropagation basically says, and this was something which was invented in, the concept was, came up with in University of Toronto about a couple of decades ago. And this really made a big change on neural networks, deep neural networks. So you're doing backpropagation using the concept of gradient descent, okay, which is something I've already spoken about, and that changes the weights of this neural network. So it changes the weights in such a way that the error is minimized. Okay, so you give it a whole bunch of pictures of elephants, it tries to minimize it, it changes the weights in such a way that eventually next time you give it a new picture of an elephant, it is able to identify it as an elephant. Okay, so this particular output will be large, this particular output for a mouse will be small. So it knows it can now differentiate between mice and elephants. Okay, so that's basically the whole concept of neural networks, and that's how it works. And so if you want to just play around with this, for example, I'm trying to differentiate between different categories of data. In this case, I don't have elephants and mice. I just have blue dots and orange dots and blue dots. Okay, so I'm trying to differentiate it, and I'm going to use a very simple neural network initially, which comprises of a single hidden layer in the center and just one neuron. Okay, and it still works. Okay. But if I try to do something slightly more complex, for example, I now have a slightly more difficult pattern. So I have blue dots in the two-dimensional space, and they're not linearly separable. Okay. So now if I do a training on this, I'm going to start it off. So let's say I start it off. And as you can see that it's trying to draw a linear line between these two. Okay. And you can see the losses over here, which is basically the error function. Okay. And here is the epochs. These are the iterations. It's trying to do an iteration. So if I change the learning rate to be really large, it'll go really fast. But if I train the learning rate to be extremely small, so for example, if I make the learning rate extremely small, then it's just going to take forever. Okay, so I want to make the learning rate somewhat large so that it progresses relatively fast. Okay, and as you can see that this is the error function in time as it's reducing. So it's not able to, with a single neuron, it's not able to do this classification very well. Okay. Now, what happens if I add another neuron and I do the training again? So you can see it's a little better. Okay. What happens if I add another neuron? It's getting close to perfect. Okay. So if I keep on adding more neurons, now this is close to perfect. Okay. Now notice what each one of these neurons is essentially learning. Okay. Each one of them is doing a linear function. This neuron over here is learning to differentiate between these two spots. Each one of them is learning a different function, but when they all put together, they can differentiate the 4 areas. Okay. Let's take a slightly more complex example here. So here is a more complex example, and it's working fine even with 4 neurons. But if I started off with a single neuron, it's not able to differentiate. Okay, I add another neuron. It's doing better, but sorry, I added another layer. I'm going to add another neuron, and then it does that pretty well. So now it's doing 3 linear functions, and the triangle in the center is being differentiated, right? But if you look at a more complex example, so something like this, then it becomes very difficult, because this is what real spaces are like, right? So if you have a giraffe in there, it's not going to be just blue dots and orange dots. It's going to be something more complex. So if you try to do this, it doesn't work very well with a single layer. Okay, you need to add more layers, and that's where deep neural networks comes in. Okay, so you're adding more and more layers, and you can add more neurons in each layer. Okay, so I can make it more complex, and I can see, well, will it eventually work or not? Okay, and you can try this out. And so, unfortunately, deep neural network is somewhat of a black box. And that's the biggest problem with this algorithm, is that you don't really know why it works. Okay, you simply put in more and more layers. That's what the usual stands for. You try to put in more layers, you try to do a brute force solution, and you just hope that at some point it will work. Okay, but then generally there is a methodology to the madness, as I say. Okay, and people do have better algorithms, and they know that these algorithms work better, and that's why some of the people who are gurus in this field, they end up at Facebook and Google, and they get paid tons of money. That's because they know how these algorithms work, and they can differentiate between a dumb algorithm and a better algorithm.